Welcome back to the discussion of spatial networks query processing and algorithms. In the last video, we saw the big picture of query processing. Databases often like to have a few building blocks which are frequently used, and for each building block they like to have multiple algorithms so that they can pick and choose. Okay. In the last module, we also saw algorithms for connectivity query, and in this module we will try to look at two algorithms for shortest path queries. Okay. So at the end of this module, we should be able to name those two algorithms and also compare their behavior. So in terms of shortest path, the basic common algorithm is an iterative algorithm. It goes into a loop, and in each iteration of the loop, it essentially looks for most promising direction, right? So it keeps a set of descendant which we have visited so far, and it picks the most promising one. But the ranking differs between the algorithms. So if we start with the older algorithm, Dijkstra's algorithm, then it picks up the closest descendant to self. It may not look intuitive, but it's a general algorithm. It works in many graphs. Okay. Now A star, which came from artificial intelligence, may look a little smarter, and it tries to pick a descendant which is closest to the destination, right? And you may wonder, why didn't Dijkstra do that? And the answer is, in some sense, it's not that easy to figure out which descendant is closest to the destination, because the future is not known. We don't know if there are the shortest path or the most direct paths may be broken, right? You may have to go around an obstacle. So in case of A star, you need some heuristic to kind of do this focusing, and that becomes very domain dependent. Fortunately for us, such heuristics are easy for road maps because they are embedded in Euclidean space, and straight line distance estimations has the right set of property to make A star shine. But in general, if you are in some other networks like electricity distribution and so on, it might be worthwhile to look at both algorithms. Okay. So essentially, we looked at the most promising descendant, and once we have visited that descendant, we can update the path to that descendant. And in addition, we may find additional descendant which are reachable from there. Okay. So we keep looping till the destination node is expanded, till that becomes the most promising node, and at that time we have found shortest path. Okay. So let's first look at the behavior, and we can later on look at the assumptions or why this is correct and so on. Okay. So we are going to show you a small animation. Let's suppose we have this very simple graph, a grid graph. Again, not very unrealistic. If you live in Manhattan or some other downtowns, there are grids like this, maybe a few more one ways that we are not showing. And in this, suppose we are starting from this red node, which is B, and trying to go to this upper right node, the green one. Okay. So we are going to show you the behavior of Dijkstra and A star side by side. Okay. So in the first iteration, they behave very similarly. They both start from the red node and they list the neighbors. There are three neighbors here, and A star, only two are shown as yellow, but it also will look at this lower left one. So all immediate neighbors are considered. Okay. The behavior changes in the next iteration. Now if you think about what Dijkstra will do, it's going to pick one of these neighbors which is closest to the start node, and in this case they are all pretty much tied. You can pick any one of them in case of Dijkstra. But in case of A star, these two neighbors are closer to destination, the green one, than this particular lower left one, right? So A star is going to pick one of these two. It will never pick that. Okay. So once they have made their choices, they will visit that node and add more neighbors. So in case of A star, the only thing that will be added is this node, because that's what is connected to here, and based on that, this is added because it's also closest to the destination. See, these nodes are also connected to other nodes, but if you look at the total distance, this one will win out. Okay. Whereas Dijkstra can only see the distance to self. It doesn't know which of these nodes is closest to destination, so it can pick any one of them. So we have shown all of them in yellow. Okay. The next iteration, it continues. A star, again you see, is focused. It's keep picking nodes which are closer to destination, whereas Dijkstra is kind of going in a breadth first search manner. So you go further, another iteration, and now A star has actually reached the destination, having expanded a small set of nodes which all seem to be somewhere near the straight line path. Okay. Whereas Dijkstra still is ongoing, it will have few more iterations till it reaches, and you can kind of see that it has a more breadth first search behavior. It looks at a lot more nodes. Okay. Okay, so once we have this sense, we can also try to quickly look at the formal properties which makes these algorithms work. Okay. So, both of these algorithms actually follow a very general algorithm design paradigm in computer science called dynamic programming. Some of you probably took algorithms course and you probably know that paradigm. Okay. A special example of that paradigm is subpath optimality. So, essentially if road maps and other transportation network, they have some very nice properties. They basically have the simple property where edge costs are positive. Okay, you never have a negative distance. They are additive and they are also fixed. Okay, so we are ignoring time variation altogether here. So, under these properties, essentially if I look at a optimal path from node A to B and let us say it goes through C, then the subpath going from A to C will also be optimal, and that essentially underlies the basic behavior of this algorithm. It guarantees optimality. Okay. In addition to this, if for A star you need one other property. Remember, we have to guess which descendant is closest to destination. So, this guess usually comes in the form of a heuristic mathematical function. For example, in Euclidean space like road maps, you can estimate straight line distance to be your guess. Okay. And that straight line distance has this nice property of being underestimate, because you can never beat straight line on a planar surface, right? And you need that kind of a properties for A star to give you the correct solution. And designing these heuristic functions takes effort and they depend on the domain, but fortunately for spatial network, the straight line distance does pretty well. Okay. Great. So, this hopefully gives you a sense of two shortest path algorithms, A star and Dijkstra. They are both very popular, but in addition, people have gone further and tried to tune these algorithms to become even faster. People have added shortcuts and they have looked at hierarchical algorithms, and perhaps through reading list or another video we will give you a sense of some of those. Okay. Just to wrap up, again this module we looked at shortest path algorithm, and together with the previous two modules we gave you a sense of physical data model which covers data structures and algorithms underlying the shortest path and connectivity query. Thank you, and hopefully we will see you in the next module.